There is a scar in your DNA that you cannot see. Scientists call it a genetic bottleneck, a place where human diversity suddenly narrows. It's as if somewhere in the deep past, our entire species was forced through the eye of a needle. When scientists map the human genome, they find something strange, something that shouldn't be there. We don't have enough variety in our genes. Here's how strange it is. Chimpanzees, who share 98% of our DNA, have more genetic diversity in a single group of 50 individuals than exists in all 8 billion humans alive today. Think about that. 50 chimps in one forest have more genetic differences than every person in New York, Tokyo, Lagos, Mumbai, and Sao Paulo combined. We are, all of us, every race, every culture, every continent, as genetically similar as siblings. It's as if, once upon a time, we all came from the same handful of survivors. The evidence is written in every cell of your body. Somewhere in our history, perhaps 73,000 years ago, a time equal to just 3,000 human generations, something nearly erased us. Not a war, not a disease, not an ice age that slowly crept across continents. Something sudden, something absolute. An event so terrible that it reduced our ancestors to perhaps 10,000 individuals scattered across the entire planet, maybe fewer. Some scientists think the number might have been as low as 1,000 breeding pairs. Imagine that. The entire future of humanity, every thought ever conceived, every song ever sung, every child born since then, all of it depending on the survival of a population smaller than a typical high school. If just a few hundred more people had died, you wouldn't exist. Nobody would. The human story would have ended before it truly began. For decades, this bottleneck was a mystery. Scientists could see it in our genes, but they didn't know what caused it. They didn't know when. They didn't know where. And then, in volcanic ash layers across India, in ice cores pulled from Greenland, in rock layers of Indonesia, scientists found the signature of the same terrible event, a volcanic winter so severe it almost ended our species. The culprit wasn't hiding, it was sleeping. In the mountainous heart of Sumatra, beneath the peaceful waters of Indonesia's largest lake, lay the broken remnant of a mountain that once touched the sky. Lake Toba, 100 kilometers long, the distance you could drive in an hour on an empty highway, 30 kilometers wide, 500 meters deep, in places deeper than the Empire State Building is tall. A lake so massive it holds more water than all 5 Great Lakes of North America combined. But this is not really a lake. This is a grave. This is the collapsed throat of a supervolcano. And 73,000 years ago, it woke up and nearly killed the world. To understand what happened at Toba, you first need to understand what a supervolcano actually is. Deep beneath the Earth's surface, about 150 kilometers down, imagine running 1,800 football fields placed end to end. The rock is so hot, it's liquid. This molten rock, called magma, wants to rise. It's lighter than the solid rock above it, so it pushes upward, the same way a balloon filled with air rises through water. Most of the time, this magma reaches the surface gradually, feeding regular volcanoes that erupt every few years or decades. These are the volcanoes we're familiar with, cone-shaped mountains that sometimes blow their tops. But sometimes, the magma gets trapped. It pools in massive underground chambers, collecting for thousands or even millions of years. The chamber grows larger and larger, like a balloon slowly inflating underground. The rock above it stretches and bulges. Cracks form. Gases dissolved in the magma start to come out, the same way bubbles come out of a soda when you open the bottle. The pressure builds and builds and builds. When the roof finally breaks, it doesn't break gently. A supervolcano is measured by something called the Volcanic Explosivity Index, or VEI. This is a scale from 0 to 8, and each step up means the eruption is 10 times more powerful than the one below it. Mount St. Helens in 1980 was a VEI-5. It killed 57 people, flattened forests for hundreds of square kilometers, and sent ash across multiple states. Krakatoa in 1883 was a VEI-6. The explosion was heard in Australia, 3,000 miles away. Imagine standing in New York and hearing a sound from London. The tsunamis it created killed 36,000 people. The ash cloud went around the globe and created amazing sunsets for 3 years. Global temperatures dropped by more than 1 degree. A VEI-7 is called a super eruption. The 1,815 eruption of Mount Tambora in Indonesia was a VEI-7. It threw out 160 cubic kilometers of ash and rock. The ash cloud was so thick, it created what people call the year without a summer in 1816. Crops failed across Europe and North America. Snow fell in June in New England. Tens of thousands of people died from hunger. Toba was a VEI-8, the maximum rating. An eruption so large that only a handful have happened in the last 2 million years. Mount St. Helens threw out 1 cubic kilometer of ash and rock. That's enough to bury all of Manhattan under a layer 10 stories deep. Krakatoa threw out 21 cubic kilometers. Devastating. World-changing. Toba threw out 2,800 cubic kilometers of ash and rock into the atmosphere. 2,800, not 28, not 280, 2,800 cubic kilometers. Enough material to bury the entire United Kingdom under a layer of ash as deep as a tall person. Enough to cover all of Texas, knee-deep in volcanic debris. If you could gather all that ash and rock into a single mountain, it would be taller than Mount Everest, much taller. It would reach into space itself. The energy released was the same as 1 billion tons of explosives going off at once. That's the power of 67,000 nuclear bombs, the kind that destroyed Hiroshima, all exploding in the same instant. It was the loudest sound in human history. The shockwave traveled around the entire world, twice. But here's the important part. The explosion itself wasn't the real killer. The explosion was just the beginning. What came after the ash, the darkness, the cold, that's what nearly ended humanity. The warning signs had been building for centuries, maybe thousands of years, but the people living around Toba had no way to understand them. Earthquakes would have become more common in the years before the eruption. Small shakes at first, easy to ignore, then larger ones. The ground would have cracked in places. Hot springs would have appeared where none existed before, the water boiling and smelling like rotten eggs. Steam vents would have opened up on the mountain's sides, hissing and spitting. Animals would have acted strangely, elephants and tigers leaving the area, birds refusing to land, even insects seeming to avoid certain zones. The mountain itself would have been changing shape. Modern instruments can measure this. Satellites can detect when a volcano swells by even a few inches. But to the naked eye, the changes would have been subtle. Maybe the mountain looked slightly different. Maybe that ridge wasn't quite so high before. The magma chamber beneath Toba had been filling for thousands of years. The chamber was huge, roughly 70 kilometers long, 30 kilometers wide, and 10 kilometers deep. If you were standing on the surface directly above the chamber, you could walk for an entire day and still be above it. The amount of magma was around 2,800 cubic kilometers, enough molten rock to fill Lake Michigan. As the chamber filled, the rock ceiling above it, several kilometers of solid granite, began to crack. The magma was under huge pressure from the weight of the rock above it, pressure that increased every year as more magma built up. Dissolved gases in the magma, mostly water vapor, carbon dioxide, and sulfur dioxide, were coming out, creating bubbles. These gas bubbles made the magma even more explosive, like shaking a bottle of soda for 1,000 years. Finally, around 73,000 years ago, the rock ceiling couldn't hold anymore. A massive crack split the surface. In seconds, the pressure was released. You are standing on the shore of what will become Lake Toba, but right now it's just the side of a mountain, and the morning is beautiful. The year is around 73,000 BCE. You are human, as smart as anyone alive today, but your world looks nothing like ours. This is the age of ice and giant animals, and you are one of perhaps 1 million humans scattered across Africa, the Middle East, and Southern Asia. Your group is small, maybe 40 people, extended family. You speak a language that will never be written down. You know the names of every plant that will feed you, every animal that might kill you, every star in the sky that guides you home. The island of Sumatra is warm this morning. The air smells like rain and growing plants. Behind you, the mountain rises into the clouds, huge, ancient, permanent. Your people have lived in its shadow for generations. Sometimes it rumbles. Sometimes smoke comes from it. It has always been there. Your stories say it will always be there. You don't know that beneath your feet, 40 kilometers down. Imagine running a full marathon and then diving to the bottom of the deepest ocean. A chamber of liquid rock the size of a mountain range has been filling for hundreds of thousands of years. You don't know that the pressure has been building, that the rock ceiling above this underground furnace has been cracking, that the mountain has been slowly swelling like a balloon about to pop. You don't know that today. The skin of the world is going to split open. It begins with earthquakes, not the quick, sharp jolts that last a few seconds. These are different. These are the Earth's crust beginning to rip apart. The ground doesn't just shake, it heaves and rolls like the deck of a ship in a storm. Trees that have stood for centuries fall over. Rock slides thunder down the mountain. Animals run in every direction, and you run with them, following instincts older than language. The earthquakes last for hours. Your temporary shelters made of branches and leaves collapse immediately, but at least they can't crush you. You huddle together with your family, terrified, waiting for it to stop. And then the world ends. The mountain doesn't erupt, it explodes. One moment there's a mountain. The next moment there's a column of superheated gas and crushed rock shooting into the sky faster than sound. The explosion is so loud you can't even hear it. It's too big, too much. It hits you like a physical wall. The shockwave moves at 800 kilometers per hour, as fast as a passenger jet, flattening everything for 150 kilometers in every direction. That's like standing in Philadelphia and having everything between you and New York City destroyed in seconds. Forests that have stood for thousands of years are reduced to splinters instantly. The heat is so intense that the air itself catches fire. When the roof of the magma chamber collapses, billions of tons of rock fall into the liquid magma below. The gas-rich magma is suddenly released from the huge pressure that had been holding it. It's like opening a bottle of soda, but the bottle is the size of a mountain and the soda is liquid rock at 1200 degrees Celsius. The magma doesn't flow out, it explodes out. The dissolved gases expand instantly, breaking the magma into tiny pieces. This creates a fountain of ash, gas, and rock that shoots into the stratosphere at supersonic speeds. The eruption column rises at speeds over 300 meters per second. That's faster than the fastest race car. It punches through the lower atmosphere and continues rising into the stratosphere. The column eventually reaches a height of 43 kilometers, 5 times higher than passenger jets fly, well into the region where space begins. At these heights, the temperature is minus 50 degrees. The ash and gas cool rapidly, and the column spreads out sideways, creating an umbrella-shaped cloud that eventually covers an area the size of a large country. From space, if there had been satellites to see it, the cloud would have looked like a massive bruise on the Earth. If you are within 300 kilometers of the blast, the distance from Boston to Washington, you die immediately. Not from the explosion, not from the heat, from something called a pyroclastic flow. Imagine a wall of ash and gas racing across the land at highway speeds. This isn't smoke. This is crushed rock heated to 800 degrees, hot enough to melt aluminum, hot enough to turn flesh to vapor on contact. The pyroclastic flows from Toba traveled at speeds up to 700 kilometers per hour. They had not just ash, but also chunks of rock the size of cars, boulders torn from the mountainside, and trees ripped from the ground. The flows were so hot they glowed orange and red, like rivers of fire. But they weren't liquid, they were solid particles floating in gas, flowing like both a liquid and a gas at the same time. The particles were cushioned by the gas, allowing them to travel with almost no friction. This is why pyroclastic flows can travel so far and so fast. When a pyroclastic flow hits the ocean, and Toba's flows did hit the ocean on all sides of Sumatra, the water doesn't stop it. The flow is so hot and moving so fast that it literally boils the water, creating massive steam explosions and continuing across the seafloor. Flows from Toba traveled across water and reached the Malay Peninsula, crossing 30 kilometers of open ocean. When the flows finally stop hours later, dozens of kilometers from where they started, the ash settles and cools. What's left is not a landscape. It's a plain of gray stone, smooth and lifeless, covering everything that once lived. The forests, the rivers, the animals, the people, all of it sealed under meters of volcanic rock that hardens like concrete. Scientists call this rock ignimbrite. Ignimbrite deposits from Toba are found across Southeast Asia, some of them more than 600 meters thick, taller than the Washington Monument. But you are not within 300 kilometers. You are farther away, perhaps 1,000 kilometers distant, on the Asian mainland. You can see the column rising on the horizon, a tower of ash climbing into the sky, higher than clouds, higher than weather, higher than the blue itself. At the top, the column spreads out like an umbrella hundreds of kilometers wide, blocking the sun. And then the ash begins to fall. It falls for weeks. At first, it's almost gentle, like gray snow drifting down from a sky that has turned the color of concrete. You can brush it off your skin. You can shake it from your hair. But it keeps falling, and falling, and falling. Within days, it's several inches deep. Within weeks, in some places, it's taller than a person. The weight of it crushes shelters. The ash gets into everything, into food, into water, into lungs. This isn't like ash from a campfire, soft and light. This is tiny shards of volcanic glass. Each piece is sharp enough to cut lung tissue. Under a microscope, ash from Toba looks like a collection of tiny knives. When you breathe it in, it sticks in your lungs and causes scarring. Breathing becomes painful. Your chest feels tight. You cough constantly, bringing up blood. People start dying from what we would now call silicosis, a disease miners get from breathing rock dust. The ash also ruins water supplies. When it mixes with water, it forms a cement-like paste. Rivers and streams become clogged. The water that does flow is undrinkable, filled with dissolved minerals and tiny glass shards. Animals that drink the water get sick. Fish die in massive numbers, their gills clogged with ash. They can't breathe even in water. Plants suffer too. The ash covers leaves, blocking photosynthesis. It's heavy enough to snap branches. Root systems can't breathe under the weight. Within weeks of the ash fall, plants across a vast area begin to die. And when the plants die, the plant-eating animals begin to starve. And when those animals die, the meat-eating animals follow. The entire food web collapses. The ash falls across an area the size of India that's more than 3 million square kilometers. If Toba erupted today, ash would fall on countries from Pakistan to Vietnam, from southern China to Indonesia. More than 2 billion people would be directly affected by the ash fall. In places directly downwind of the eruption, mostly to the west and northwest, the ash piles up 15 meters deep. That's as high as a 5-story building. Entire ecosystems are buried alive. Forests that took thousands of years to grow are buried in gray stone in a matter of weeks. The landscape looks like the surface of the moon, gray, lifeless, cratered. The ash layer is so thick and so widespread that 73,000 years later, scientists find it everywhere from the Arabian Peninsula to the South China Sea. It's called the youngest Toba tuff, or YTT. When archaeologists are digging and they hit a layer of gray ash with a specific chemical signature high in silica, with distinctive trace elements, they know exactly when they are in time. 73,000 years ago. But the ash is not the worst of it. You are covered in ash and starving, but you are still alive. You have moved south, away from the gray zone, looking for food, looking for anyone else who survived. The sun is gone. Not hidden behind clouds, gone. The sky is a solid gray dome, and you can barely tell day from night except for a slight lessening of darkness at what used to be noon. The temperature is dropping. You can see your breath in the air. This is Southeast Asia, where it's supposed to be hot all year round, and you can see your breath. The volcanic winter has begun. When Toba exploded, it didn't just throw ash into the air. It also shot about 5 billion tons of sulfur dioxide into the upper atmosphere. To understand how much that is, imagine every human being on Earth, all 8 billion of us, and then multiply that by 600. That's the weight of sulfur dioxide. Sulfur dioxide is a gas at normal temperatures. But at the cold temperatures of the stratosphere, the layer of atmosphere between about 10 and 50 kilometers up, it acts differently. The stratosphere is very dry, but there's still some water vapor up there. The sulfur dioxide reacts with this water vapor and with oxygen to form tiny droplets of sulfuric acid. Each droplet is microscopic, smaller than a red blood cell, but there are trillions upon trillions of them. These sulfuric acid droplets create what scientists call an aerosol layer. An aerosol is tiny particles floating in gas. The aerosol layer from Toba spread around the entire planet within weeks, carried by winds that blow at hundreds of kilometers per hour. The layer eventually covered the Earth like a blanket. Here's the critical part. Sulfuric acid droplets are reflective. They're shiny. When sunlight hits them, about half of it bounces back into space instead of reaching the Earth's surface. It's like putting up a giant mirror between the Earth and the Sunday. The Earth dimmed. Scientists estimate there was a 20 to 30% reduction in sunlight reaching the surface. That might not sound like much, but it's huge. Plants need sunlight to grow. Animals need plants. Everything depends on solar energy. And with less sunlight reaching the surface, the temperature dropped and kept dropping. Within weeks of the eruption, average global temperatures fell by 3 to 5 degrees Celsius. That might not sound like much, but it's huge. It's the same amount of warming humanity has caused since we started burning coal and oil, but in reverse, and happening not over 150 years, but over a few weeks. 3 to 5 degrees is the global average, but the effects weren't the same everywhere. Some regions got hit much harder. In the northern hemisphere, which was already heading into winter when Toba erupted, temperatures in some areas dropped by 15 degrees. 15 degrees. That's the difference between London's climate and northern Norway's climate. That's the difference between a forest and Arctic tundra. Ice cores from Greenland, long cylinders of ice drilled from glaciers that preserve a year-by-year record of past climate, show a dramatic spike in sulfate around 73,000 years ago, exactly matching the Toba eruption. The sulfate levels are literally off the charts compared to any other volcanic eruption in the ice core record. The volcanic winter lasted for 6 years. 6 years without full sunlight. 6 years when plants couldn't grow properly. The wild fruits and nuts and roots that humans gathered didn't produce food. The animals we hunted started dying from starvation. Killing frosts reached into tropical areas that had never seen frost. Ocean temperatures dropped too. The oceans are like a massive heat battery. They absorb heat from the sun and release it slowly. But even the oceans couldn't protect against 6 years of reduced sunlight. Sea surface temperatures in the tropics fell by 3 to 5 degrees. In higher latitudes, they fell even more. This had cascading effects on ocean currents, weather patterns, and marine life. Rainfall patterns changed dramatically. With cooler temperatures, less water evaporated from the oceans. Less evaporation meant fewer clouds and less rain. Monsoons, the seasonal rains that millions of people and animals depend on, weakened or failed completely. Droughts spread across regions that normally got abundant rainfall. Scientists can see evidence of this in lake sediments from around the world. Lakes in Africa, India, and China showed dramatic changes around 73,000 years ago. The lakes became shallower. Some dried up completely. The sediments show increased erosion when plants die. There's nothing to hold soil in place, so it washes away. And when the volcanic winter finally ended, when the sulfuric acid droplets finally fell out of the stratosphere and rained down as acid rain, which itself caused damage, the planet didn't bounce back to normal. It slid directly into a full ice age that would last for 1,000 years. Ice sheets that had been slowly shrinking started growing again, spreading down from the North Pole like frozen bulldozers. The ice eventually covered Canada, Scandinavia, and northern Russia under sheets 2 to 3 kilometers thick. That's thick enough to bury a mountain. The weight of the ice was so great it actually pressed down on the Earth's crust. With so much water locked up in ice, sea levels dropped by 120 meters, about the height of a 40-story building. Coastlines moved outward by hundreds of kilometers. Land bridges appeared between continents that had been separated by ocean. You could walk from mainland Southeast Asia to Java and Borneo. Ocean currents changed direction and strength. The Gulf Stream, which keeps Europe warm today, weakened significantly. The thermohaline circulation, the great conveyor belt of ocean currents that moves heat around the planet, was disrupted. The planet's entire climate system had been knocked off balance and thrown into chaos. And humans, already struggling, already on the edge, had to survive it all. You are cold. You have been cold for so long that you can barely remember what warmth feels like. It has been 3 years since the sky turned black. The ash has finally stopped falling. The sun is visible now, sort of a pale disk behind gray haze, giving light but almost no heat. But nothing has gone back to normal. The world is dying around you. The plants that survived the ash are dying in the cold. The few animals you see are thin, starving, their ribs showing through their fur. Your group, which once had 40 people, is down to 12, then 9, then 6. You haven't seen another human group in over a year. You don't know if they're dead or if they've moved on, searching for food that doesn't exist. You don't know if your group is the last one alive, or if somewhere, in the few warm places left on Earth, other groups are fighting to survive just like you are. Food is the constant obsession. You're eating things your ancestors would never have considered food: bark, roots so tough they're almost impossible to chew, insects, anything with calories. You've become an expert at figuring out which plants won't kill you, which mushrooms are safe, which bugs are nutritious. Your body has adapted to near starvation. You've lost weight you didn't have to lose. The night sky is different now too. With less moisture in the air, the stars are impossibly bright. You can see the Milky Way as a river of light stretching from horizon to horizon. On clear nights, and most nights are clear now, you can see your shadow cast by starlight alone. It would be beautiful if it weren't so terrifying. This is the bottleneck. This is the moment. This is when the future of humanity hangs by a thread so thin it's almost invisible. Scientists who study genes have developed smart techniques for reading history in our DNA. Every person alive today carries, in every cell, a complete copy of the human genome, about 3 billion base pairs of DNA, arranged in 23 pairs of chromosomes. This DNA is like a book, and mutations are like typos that build up over time. By comparing the DNA of people from different populations, scientists can work backward, building family trees that stretch back thousands of generations. What they've found is startling. Humans show dramatically less genetic diversity than we should, given how many of us there are and how spread out we are. When scientists compare any two humans chosen at random from anywhere on Earth, their DNA is, on average, 99.9% identical. The 0.1% that varies is what makes you look different from someone from China or Nigeria or Peru. But 0.1% is incredibly small. For comparison, two chimpanzees from the same forest in Africa typically have more genetic differences between them than exist between any two humans. A group of 50 chimps has more genetic variation than all 8 billion humans combined. This shouldn't be possible unless, at some point, human population size crashed to a very small number. The data points to a severe bottleneck happening between 50,000 and 100,000 years ago, with the most likely date around 73,000 years ago, exactly matching the Toba eruption. Different studies have guessed the bottleneck population at anywhere from 1,000 to 10,000 breeding individuals, though some research suggests it could have been as low as a few hundred. 1,000 breeding pairs means 2,000 individuals total. That's the entire human population of Earth, reduced to fewer people than attend some high schools. 2,000 people to carry forward the entire genetic heritage of our species. If you gathered all the humans alive at the bottleneck into one place, they'd fit inside a large movie theater with room to spare. We came within a whisper of going extinct. Every model of population genetics says that a population this small, facing conditions this harsh, should not survive. The genetic diversity is too low. There aren't enough different genes to adapt to changing conditions. Inbreeding becomes unavoidable, leading to health problems. Disease can sweep through a small population and kill everyone. One bad winter, one long drought, one encounter with a predator or a hostile group, and that's it. Game over. But we didn't die. Somehow, impossibly, we held on. The survivors were not random. They were the ones who made it to special places scientists call refugia. These were small pockets of land where the climate stayed relatively stable, where life could continue even as the world around it froze. In Africa, the main refugia were in the southern tip of the continent, modern-day South Africa, and parts of the Great Rift Valley in East Africa. These areas had unique features that protected them against the worst of the volcanic winter. The southern tip of Africa benefits from being surrounded by water on three sides, and ocean temperatures don't change as fast as land temperatures. The region also has incredible variety in terrain, with mountains, valleys, and coastlines creating numerous small climates. When conditions became impossible in one area, people could move just a few dozen kilometers and find better conditions. The Great Rift Valley in East Africa also served as a refuge. The valley runs north-south for thousands of kilometers, creating a natural corridor with varied elevations and climates. Lakes in the valley provided reliable water. The valley walls protected against harsh winds, and the varied terrain meant there were always some areas with better conditions than others. In Asia, the primary refugia were along coastlines and on tropical islands that remained warm enough to support life. The Malay Peninsula, parts of Indonesia, coastal India, these areas, while certainly affected by the eruption, didn't experience the same extreme cold as continental interiors. The humans who survived in these refugia were not necessarily stronger or faster than those who died, but they had certain advantages. They were adaptable. When their traditional food sources disappeared, they learned to eat other things. Archaeological evidence from this period shows increasing use of marine resources. People started eating shellfish, catching fish, even hunting marine mammals. These coastal resources were more reliable than land-based ones during the volcanic winter. They were innovative. Stone tools from this period show increased complexity. People developed new techniques for making sharper, more efficient tools. They invented new weapons for hunting. They created better methods for making fire and keeping it going. They developed new strategies for finding and processing plant foods. They were cooperative. Small, scattered groups couldn't afford internal conflict. They had to work together, share resources, share knowledge. There's evidence that trade networks expanded during this period. Stone tools made from raw materials found hundreds of kilometers away, suggesting groups were keeping in contact and exchanging goods and information. And they were resilient. They refused to give up. When faced with conditions that should have killed them, they found ways to adapt, to innovate, to survive. Slowly, over thousands of years, the population began to grow again, not quickly. The genetic bottleneck had reduced our diversity so much that recovery was slow. But the survivors had children, and those children survived. And gradually the number of humans on Earth began to increase. The genetic legacy of those survivors is visible today. When scientists trace maternal lineages using mitochondrial DNA, which is passed down only through mothers, they find that all humans today can trace their maternal ancestry back to a relatively small number of women who lived in Africa around this time. Similarly, Y chromosome studies, which trace paternal lineages, show that all men today descend from a relatively small number of men from the same period. We are all cousins, more closely related than we like to admit. The genetic differences we use to define race are vanishingly small, less than the genetic variation within any single African population. Every person you see, regardless of what they look like, is your relative, your family, a descendant of the same tiny group of survivors who made it through the fire and ice. But something else happened during the bottleneck, something unexpected, something that might have actually helped our species in the long run. When a population goes through a severe bottleneck, it doesn't just lose genetic diversity randomly. Certain traits, if they're helpful under the current conditions, can spread very quickly through a small population. If a mutation appears that helps with survival, better cold tolerance, more efficient metabolism, enhanced thinking abilities, that mutation can become common in just a few generations when the population is small. Some anthropologists believe that the Toba bottleneck may have sped up the development of modern human thinking. Before Toba, humans were modern in body. We looked like people today, but our behavior was less complex. After Toba, we see an explosion of innovation, better tools, art, jewelry, evidence of symbolic thinking, long-distance trade, complex social organization. It's possible that the harsh conditions of the volcanic winter selected for increased intelligence, creativity, and social cooperation. The groups that survived were the ones who could solve problems, who could innovate, who could work together effectively. These mental and social skills may have been refined and concentrated during the bottleneck, then spread rapidly as populations recovered. The catastrophe didn't break us. It may have shaped us into what we are today. 73,000 years later, Lake Toba is one of the most peaceful places you could visit. Tourists come to its shores to relax. They take photographs of the sunset reflecting on the water. They swim in the crystal blue depths. The lake is surrounded by green hills and rice fields that grow in perfect terraces up the mountainsides. Local people, the Batak people, live in traditional houses with distinctive curved roofs. They farm and fish, going about their lives. They tell old stories about how the lake was created, tales of a giant fish and a poor man and a magical transformation. They don't realize how close those stories are to the truth. The lake itself is beautiful but strange. It's not a normal lake, it's a caldera lake, formed when the magma chamber beneath the volcano emptied during the eruption and the ground above it collapsed. The caldera is roughly 100 kilometers long and 30 kilometers wide, the largest volcanic caldera on Earth. In the middle of the lake sits Samosir Island. Toba has had at least 4 major eruptions in its history. The one 73,000 years ago was the most recent, but not necessarily the largest. The volcano isn't dead, it's sleeping. Studies show that the caldera floor is rising slightly, just a few millimeters per year, but measurable. Seismometers detect small earthquakes regularly, about 20 to 30 per month, showing ongoing magma movement. Hot springs around the lake show that heat is still rising from below. Will it erupt again? Absolutely. The question is, when? Geological timescales are long. The previous 3 major eruptions of Toba happened at roughly 400,000-year intervals. The last eruption was 73,000 years ago, so by that schedule, we have another 327,000 years before the next super eruption. Probably. Volcanic systems don't follow precise schedules. Even if Toba doesn't erupt soon, there are other supervolcanoes around the world that could. We've colonized every continent except Antarctica. We've reshaped the planet. We've developed technologies that would look like magic to our ancestors. We've been to the moon and sent probes to the edge of the solar system. All of it stems from those few thousand survivors who refused to give up 73,000 years ago.